In 1927, Werner Heisenberg introduced his famous uncertainty principle. Now, this is probably something that you've heard of, but being able to wrap your mind around it is something a little bit more. Remember our double slit experiment where we sent single electrons towards the two slits and it somehow formed an interference pattern on the screen? Remember, it didn't start out that way. This was not an immediately recognizable pattern until the experiment had gone on for quite some time. The markings on the screen did not start out as a pattern, but as random hits of the electron. As we kept shooting electrons toward the screen, we finally started to see that interference pattern emerge. Let's go back to our single slit for a moment and look at how the electrons create the pattern there. There's a very wide central bright fringe that is surrounded by much smaller bright fringes that fade away on either side. These bright fringes are the places where the electrons will appear on the screen after traveling through the slit. So an electron could hit here along the screen, or here. Of course, the central part of the big bright fringe is the most likely place for an electron to hit. So again, if our electrons were just behaving like particles, they would all appear right there in the middle, and the image on the screen would only be as wide as the width of our slit. Instead, only about half of them do, while the other half are most likely on either side, and the pattern ends up being much wider than the width of our slit because of diffraction. Since we are interested in figuring out where the electron is going to hit the screen, we want to find where the bright fringe ends. Remember from our study of wave optics, we can say that the first dark fringe, or the end of the central bright fringe, is equal to the width of the slit times the sine of the angle from the center, and this is equal to the wavelength of the electron. Now, our electrons are coming in the slit with some momentum, and if we assume that they are fired directly horizontally to the slit, then that momentum is simply all carried in the horizontal direction. It is possible that the electrons will continue on with this horizontal momentum and hit the screen directly behind the slit. But we also know that some of those electrons do not travel in a completely horizontal manner. Some will be deflected and travel at some angle towards the screen. So not only does the electron now have momentum in the horizontal direction, but it also has a y component to it. The thing is, we don't know. As soon as an electron travels through the slit, we don't know what the momentum will do. We do know that it will have some horizontal momentum, but we don't know how much, if any, y momentum it will have. Therein lies the uncertainty. So the fact that there is, in fact, a bright fringe and not a single line on our screen tells us that there is uncertainty in the y direction. We are going to give the momentum uncertainty a designation of delta p. Now, this is not the same thing as a change in p. We just use delta to describe both situations. So delta in the quantum world refers to the uncertainty. Want some more? There is also an uncertainty associated with where the electron actually is. The electron is moving through the slit, but we don't know exactly where. It could be right in the middle, it could be closer to one of the edges, but we aren't sure. We do know, however, that its position is limited to the opening it passes through. So we can say that the uncertainty in the y position is roughly equivalent to d. So the width of the slit is what limits our uncertainty. Remember, wave optics tells us that if we have a small slit, our diffraction pattern will be a larger, more spread out central bright fringe. On the other hand, a larger slit will produce a steeper, less spread out central bright fringe. This is not what you might expect. The better idea we have of where the electron was when it went through the slit, the more uncertain we are about where it hits the screen. So a smaller slit results in a much wider area where the electron could hit. On the other hand, the more uncertain we are about where the electron is moving through the slit, the more accurately we can predict where it will hit the screen. So if we know one thing, we can't know the other. Going back to our math, we can assume that we are talking about small angles. Looking at our momentum components, we can see that a really small angle will make the hypotenuse of that triangle and the x component nearly equal. Enough that it lets us say that the sine of the angle theta is equal to the tangent of the angle theta. So we can write both of these as the uncertainty of the y component in our electron momentum divided by the momentum in the x direction. From our wave optics equation, we can also say that the sine of angle theta is equal to the wavelength over the width of the slit. Now, remember de Broglie gave us a nice equation to explain the wavelength of an electron with respect to its momentum. This fits in with the momentum coming into the slit, and so describes the momentum in the x direction. We can rearrange the equation for the x momentum and say that Planck's constant over the wavelength is equal to the x momentum. And we're going to use this to plug it into that p sub x spot. We also know that the width of our opening is equal to delta py, so we can substitute that in as well. So we get a new equation that says that the wavelength of our electron over the uncertainty of the y position is approximately equal to the uncertainty of the y momentum times the electron wavelength over Planck's constant. Rearranging this, we can cancel out our lambdas, and we find that Planck's constant is approximately equal to delta y times delta py. Of course, that approximately equal sign is a bit problematic when you're talking about actual mathematics. There is some much more complicated math that we could do to get rid of it, but we're not. Suffice it to say that the uncertainty of the momentum in the y direction times the uncertainty of the y position must be greater than Planck's constant over 2 pi. This is the Heisenberg uncertainty principle. It tells us that we cannot measure both the position and the momentum of an object precisely at the same time. The more accurately we try to measure the position, the smaller delta y will be. As delta y decreases, the uncertainty in the y momentum must increase, which makes us even more uncertain as to the object's momentum. Now, this doesn't mean that we can't take precise measurements. For example, we could measure the position of the object exactly, but then its momentum would be completely unknown, and we would have no idea where it would be a moment later. The quantity h over 2 pi is used quite often in quantum mechanics, and so it gets its own designation of h bar. We can actually work this out since h and pi are definite values, so h bar is equal to 1.055 times 10 to the negative 34th joule seconds. Another useful form of the uncertainty principle lies in the energy and time of an object. This says that the uncertainty and energy in the system relates to the uncertainty in the time it takes to measure the energy. The quantity of these two uncertainties is equal to the h bar. So if the time it takes to measure the energy is very precise, then the uncertainty in the energy increases. So by precisely measuring the time, we mean a smaller and smaller time period. Then we would have less and less of an idea of the actual amount of energy.